get started today? So we've learned a lot about derivatives so far. Yeah, we've got our transcendental derivatives, sine, cosine, dx, natural log x. So those you got to have locked in your memory. Okay. Hopefully you know those. We're going to learn some more next time, not today, but we'll add to that list. Then we also know a couple of derivative rules, like the power rule. And we already kind of knew how to deal with addition and subtraction. Last time we learned how to deal with product of functions. And today we're going to learn how to deal with a quotient of functions. So basically, this will be the fourth and final operation with functions that we can find the derivative of. Yeah. So let's just get right to it here. Let me go ahead and give you the quotient rule. So if you've got two functions that are being divided, and instead of f and g, I thought I might use t and b instead for top and bottom. Okay, so let's say you've got a function that is a quotient of two sort of lesser functions. All right, we want to find the derivative. And the reason why I want to use t and b instead of f and g here is because I've seen pretty often on the AP test, they try to, I don't know if trick you is the right way to put it, but they'll like sometimes put the g on top and sometimes put the f on top. And they're not very consistent about that. So I don't want to give you a rule in terms of f and g and have you memorize that thinking that f is always on top or g is always on the bottom. So I don't want to do that. Instead, I thought it might be make more sense to use t and b for top and bottom, for numerator and denominator. So anyway, here's how you would differentiate this. And really, this is just a variation on the product rule. You can actually derive this, rather than differentiate, derive this rule from the product rule. If we have time at the end, maybe we can kind of go through that. But let me just go ahead and give you the quotient rule right up front here. So you're going to differentiate the top. Well, let me just say, we leave some room for a fraction here. You differentiate the top, multiply that by the bottom, minus the top times the derivative of the bottom, all divided by the bottom squared. So this one's a little bit more challenging than the product rule. Obviously, there's more going on. But the other thing that makes it a little bit more challenging is you do have to remember the order here. With the product rule, since we were adding two expressions, the order didn't matter, right? You could do f prime g plus g prime f or the other way around. That didn't make a difference. Here, it will make a difference because one of these expressions is positive and the other one's negative. Yeah, so it's going to matter which one's which. So what I'm going to be looking for, like in your setup, like when you're taking the test, it's a free response question or something like that. The number one thing I'm going to look for to see, hey, are you doing this right? Is this function the same right here? That's really, I think, the easiest way to kind of keep it straight is to know that in that first expression, the bottom function should be the same as the bottom function you're using in the denominator. So that should be like, kind of what you look for as far as like the sign that you're setting it up correctly. Those two functions should be the same. Any questions before we start going through some examples here? Because really that's all we're going to do today is just work through some examples. Okay, well, now we can kind of practice this, yeah? Okay, so because we've got multiple functions going on here, it's a little bit more involved in the product rule. It might be worth up front just kind of declaring what the functions are that we're using and what their derivatives are. And that way, when you go to plug everything into the quotient rule, it's just a little simpler that way. So like for number one, my top function is just 3x to the fourth. Right, and my bottom function is x squared minus 6. Okay, so what's the derivative of the top? Yeah, 12x cubed, good. And what's the derivative of the bottom? 2x. So I'm just asking for the derivative, not to actually plug anything in yet. Okay, so now that I've got those components, I can start to plug those into our quotient rule. So our derivative of f is first the derivative of the top. Okay, so that's the 12x cubed times the bottom function. So times, I guess I should use parentheses here, x squared minus 6 minus the top function, 3x to the fourth, times the derivative of the bottom, so 2x, all over the bottom squared. Okay, and if this was a free response question, I'd be happy with that. Yeah, that's a good answer. But if it's a multiple choice, you can almost be guaranteed that this is going to be simplified. So let's just kind of go through the simplifying the distributive property just so we don't get rusty with all that. Can we do what now?
You can cancel out the top and one of the
unfortunately not, because that x squared minus 6 is not a factor of this other expression here. So it's got to be a factor of each one. So you can't just cancel one of those out. Yeah, that is quite unfortunate. But that, like looking at your first step or your setup, this is what I'm looking for. I'm looking to see that these are the same. If those are the same, then you know you're setting this up right. Okay, so let's try to simplify this a little bit. We'll distribute the 12x cubed. So that'll be 12x to the fifth. And let's see, 6 times 12, 72. Yeah, thank you. And then we've got negative 3x to the fourth times 2x. So minus 6x to the fifth. All over. And then we've got to multiply x squared minus 6 by itself. So x squared times x squared is x to the fourth. X squared times negative 6 is negative 6x squared. But we have two of them, so negative 12x squared. And then finally, negative 6 times negative 6 is positive 36. Whew. And then we do see we've got one more little thing that we can combine here and simplify just a tad here, is these got two x to the fifth terms. All right, so we can combine them. They're like terms. 12 minus 6 is going to be 6. So we got f prime x equals 6x to the fifth minus 72x cubed. I don't think we need to go any further than that. So the red box is what I'm happy with, for the free response. This is what your multiple choice answer choices are more likely going to look like. And it might even be factored. I mean, it's really hard to say with the multiple choice, how far they're going to go. You can factor out a GCF on top. Is that denominator factorable? Let's see. 9 and 4. It's not going to work. 12 and 3. No.
pull out a 6 from the top.
Oh, 6 and 6. Yeah. Okay. So possibly they'll factor this out. Yeah. I mean, this could keep going, right? Does 6 go into 72?
Yeah, 12.
12 times? Okay. So we can factor out a 6x cubed. So that'd be x squared minus 12, right? And then the denominator would be x squared minus 6 times itself, right? Yeah, you don't necessarily need to take it that far, but you could. It kind of looks like that, right? I mean, it's not exactly, but yeah. This one, yeah, the denominator, yeah, it's kind of pointless, right? It's already kind of factored there. Yeah, I'm guessing you're going to probably see it in standard form.
We don't just have to try 20 different versions of the same thing.
Yeah, they're all logically, and that's why in the free response, like that's part of the reason why you're sort of allowed to not simplify, is because there's infinitely many ways we could represent this, and none of them are wrong. Yeah. Okay, let's try number 2. So here we've got our top equation is x to the fifth. And our bottom equation, sine x. All right, so what's the derivative of x to the fifth?
5x.
All right, good. 5x to the fourth. And then derivative of sine? Cosine. Okay, now we're just going to kind of go through the motions here. Plug in the t prime, the b prime, everywhere they go. So the derivative of h will be the derivative of the top, so 5x to the fourth, times the bottom, so sine x. Remember, that is what I'm looking for to be the same. Look for that same expression on the bottom. Minus the top, so that's x to the fifth, times the derivative of the bottom, so cosine x. Divided by bottom squared, so sine squared. We could see it once again. These are the same, right? We got the sine x. So that's what I'm looking for, right? That's how you know you're kind of setting this up right. Is if in that first positive term, I see that bottom function. Any questions so far? I'm not even going to bother going further with that one. Just leave it like that. I guess you could factor out x to the fourth would really be the only manipulation that would even be worth considering, I guess. There's not really much else you could do. Yeah, maybe there's like you could rewrite sine squared as like 1 minus cosine squared or do some shenanigans like that, but it's not really. Yeah, I don't think we'll really need to. Okay, number 3. At this point, hopefully you're kind of catching on here to what, it's just going to be a matter of practicing this enough so that you just know what the quotient rule is. Because, 2 or 3 problems in, we're still looking back at what the rule is. We haven't really committed it to memory yet. The more you do this, the more likely it is it's gonna settle in your head. So just keep at it here. So my top function is natural log x, which means my derivative of the top is going to be x to the negative 1 or 1 over x. My bottom function is 3x squared minus 6x. So my derivative of that, 6x minus 6. Okay, and now we're just going to go through the quotient rule. So the derivative of g is x to the negative first times 3x squared minus 6x. Oh, this simplifying is actually going to work out nicely. I'm gonna say we probably should distribute that eventually. That'll clean up really nicely. Minus the top natural log x times the derivative of the bottom, so 6x minus 6. That distributive property is not going to be as nice. It'll just have more natural logs thrown in there. Probably not worth it. Divided by the bottom squared. And you might just want to leave that squared. I don't know that it's really worth multiplying it out. I don't know. It's hard to say, how they're going to like showcase the answer choices. We could definitely do it, but I'm not going to worry too much about that. I do want to multiply this in though, because that does clean it up pretty nicely. You see some like clear advantage to distributing that in. So we get 3x minus 6, and then minus this natural log of x times 6x minus 6. I don't think there's really much else we can do. If you want to multiply out that denominator, you can. It would be 9x to the fourth minus, 18 and 18 would be 36 x cubed plus 36 again. Wait a minute, is that right? I think so. Yeah, okay. Your answer might be some variation on this too, but any questions about what we're doing so far? You guys feel okay about it? I only have a couple more problems for you. Let's do number 4. So here the top function is 6e to the x. What's the derivative of that?
6e to the.
Yep, same thing, right? And then my bottom function is x plus 5, and the derivative of that is just 1. So I have a feeling this final expression is going to be a lot simpler than some of the other ones we're seeing. Let's see how it plays out here. So the derivative of p is the derivative of the top, 6e to the x, times the bottom, which is just x plus 5, minus the top, 6e to the x again, times the derivative of the bottom, which is just 1, so we could just leave that as it is, over the bottom squared. Now on this one, you might, I'm seeing we have that 6e to the x on both expressions in the numerator. If you were to factor that out like a GCF, you'd get 6e to the x times, and then x plus 5 minus 1, which could simplify a little bit. So, there might be something to that. This just becomes x plus 4. I don't know if it's like totally worth it, but I guess it looks a little simpler. But honestly, like even if you leave it like this, that's totally fine. I mean, if you could just execute the quotient rule without doing any simplifying, that's 9/10 of the battle right there. All right, let's take a look at the back. All right, any questions so far? Kind of getting the feeling that maybe this you guys are taking this in well. All right, so we're going to use the table to answer these questions. We're still going to focus on the quotient rule here. Okay, it says if p to the x is this quotient, then what's the derivative of p at 1? All right, so the derivative of p would be, let's see if you can do it without flipping the page over. The derivative of the top, so that'd be the derivative of f times the bottom, so times x squared minus 3, minus the top, f of x, times the derivative of the bottom, which would be, I guess that would just be 2x, yeah? All over x squared minus 3 squared. I think we might have time to go through the proof on this one. But let's see. Let's see how long these take. Okay, so we've got the derivative at 1, which if we substitute 1 into all of these, it's going to give me f prime of 1 times 1 minus 3. So 1 minus 3 is just negative 2. Minus f of 1 times 2 times 1 is just 2. Oh, I guess I was too loud. Times 1 squared minus 3. So 1 minus 3 is negative 2. But squared would be 4. All right, so I just plugged in 1 into all the x's and simplified everything that I could without looking at the table. But now I'm going to use the table. Okay, f prime of 1 is negative 5. F of 1 is 4. So the two values we're going to use here are going to be these two. Oh, no, not this one. Sorry. These two. All right, so let's start plugging all this stuff in. We got -5 times -2 minus 4 times 2 over 4. All right, so we got 10 minus 8 over 4, which reduces to 1/2. Yeah, so the slope of p at 1 is 1/2. Yes, ma'am.
If this was like a free response question and like you have to like show all the steps, would you have to like do it like how you did it, like with that f comma 1 times like -2, or could you just go straight to like the -5 times -2? That makes sense.
So let me just make sure I understand your question right. You're asking if, like, we can leave out this step, basically.
Yeah.
If you understand what's happening well enough to skip this step, you are welcome to. Yeah. I will always kind of tend to show more work than is necessary. But yeah, if you are following along with what's happening, and you're just plugging in 1 and you just go straight to the table, I'm fine with that. All right. Number 6, 1 over g to the x, or 1 over the derivative of okay, so just to be clear here, this is a comma. This is not a derivative symbol. I really don't like how that got formatted. Okay, so anyway, let's find the derivative. So the derivative of m is going to be the derivative of the top. Now hold on here. What's the derivative of the top? 0. So I'm gonna write that in here, but we'll know that that's going to simplify out. So the derivative of the top is 0. The bottom function is g to the x. We know that's just going to 0 out, but I'm just going to write it just so that we're in the habit of going through the quotient rule, minus the top, which is 1, times the derivative of the bottom, over the bottom squared. All right, so we're going to plug in 2. And if you're comfortable just like going to the table at this step, that's fine. So really all we want here is the derivative of g at -2. So that's going to be 1. So we got -1 over g of -2, which is -3 squared, is 9. So that one's a little easier. Yeah.
Wouldn't the top be just 1? Because it would be.
So we got g prime of -2. So here's where g prime is. Here's -2. So g prime of -2 is +1. The reason why it turns out to be negative is because we're subtracting that term. So that minus sign is going to like basically have -1 times 1. Yeah. So yeah, it does end up being negative. Good question though. Yeah. Keep those questions coming. Yeah. The more you guys can ask, the better you're going to understand. All right. Do we need another one? How are y'all feeling about the quotient rule? Y'all want to do another example? It's pretty much the same thing. I think it's safe to skip this one. I think we've done enough. Let's just take a quick look at number 8. I'll go back and make sure we do number 7, and so that you can check to see if you just want another example. But number 8 says let f be a differentiable function with some information here. Okay, so this is like my x1, y1, and here's my slope at x equals -1. And we have another function, g of x, which is the product of f of x and 2x squared plus 3. Write the equation of the line tangent of the graph of g at the point where x equals -1. So we're going to write an equation here. We need a slope and a point. But you want to be careful here because we want the point and the slope from g, not from f. So this x1, y1 is really not what we want for our coordinate. The x is going to be -1, but the y value is going to be what we get by plugging in -1 into g. So what we really want here is g of -1. So that's 2 times -1 squared plus 3 times f of -1. And so that f of -1 equals 3, that's what that's going to come into play. Probably need some parentheses on that. Okay, so we can go ahead and evaluate this. -1 squared is just 1. 2 and 3 is 5. 5 times 3 is 15. Okay. F of -1 over here is 3. We got 5 times 3. Okay, so that's my g here. My value of g, my y coordinate. And then for the slope, what we want is the derivative of g at -1. So now we need to find g prime. Now this is not a quotient rule problem. This is just a regular old product rule. So let's just hopefully we don't forget how to do the product rule here. It's going to be 2x squared plus 3 times the derivative of f plus the derivative of 2x squared plus 3, which is 4x, times f of x. So we use the product rule to get that. And so now we can find the slope when x is -1 by just substituting in -1 here. I'm not even evaluating in my head yet. I'm just kind of replacing everything. Okay, so now we'll simplify this out. We got 2 plus 3 is 5 again, times the derivative of -1 of f, which is 1. So 5 times 1 plus -4, so -4, times f of -1, which is 3. So we have 5 minus 12. So the slope of g at -1, 5 minus 12 is -7. So now I can write that equation of the line using that same point slope format that we've used over and over again. Y minus 15 equals -7 times x plus 1. All right. Finished a little early today, so I'll go ahead and pass up the homework. You got some time to work on it. I'll go back and work out number 7. I'll just do it up here without narrating myself. That way you can at least have an extra example if you want it. But otherwise, let's use the rest of the time to work on this homework.